Oh, hi there. We're glad you're watching one of our virtual lunch presentations. We have a lot of good information that we've been accumulating over the past several years, and we invite you to look down just below here and hit the subscribe button, and the little bell will give you a reminder of when our next presentation is published here on the YouTube channel. Thanks for your support. Appreciate it. Our supporter today is Kintronic Labs, and we're very happy, as always, that they have chosen to take care of us. Kintronic Labs now has is in store facet on their website, so you can order parts anytime, day or night. But obviously, we know them. Yes, phasers. Yes. Isocouplers, yes, dummy loads, installation towers, transmission lines. I find that if you call Kintronics and you talk to Tom or you talk to Joshua, who is now the CEO, they will do everything they can to take care of your needs. And so I can highly recommend Kintronic Labs for whatever your needs are. And I think I've mentioned this before. It's amazing sometimes when stations buy a phaser from Kintronics. They're delivered, they're plugged in, and bang, they're right on. Very little has to be done in the field. So, with that in mind, today we have a very interesting discussion of grounding. And I'll just sort of preface this a bit. I was surprised to learn that the electrical code believes that 25 ohms is ground. Hello? And we'll find out why that and worse situations can be dangerous and what to do. So we have Tom LaBarge and John Belk with us today. John gave a presentation during the NAB show and shared some of that with us a week or so ago, which really was good. And now we want to focus in on it, answer your questions as to what it really means to have a ground. Tom, John?
I'll wait for John. I haven't seen him yet.
Hey, I'm here. Can you hear me by the way?
Yes, sir. Can't see you, but we can hear you.
And Tom, are you projecting the slides?
Not yours. I can't get a hold of those right now.
Okay.
So I'll look one more step, and I'll try to find it as you're talking. But you can start, and we'll go from there.
The slides I used at NAB will be the guide that I'm going through here for the moment. But what I'm hoping is that Tom can pull up some of the examples and describe some of the issues that we saw along the way. But if you don't mind, I'll just get started into what I see slide by slide to help me with the alignment. Essentially, what we discovered is that while we were looking for solutions to some lightning damage, we discovered just how far the industry has gone without much change in grounding systems and without a realization that they really should pay attention. Some of my radio friends would tell me things like, oh, we don't need a better grounding. It's good enough, always has been. And besides, everything going into the ground is just coming off of a power supply. Well, things have changed. And it's not just corrosion, but all the digital advances that are supporting all of the products that people are pushing, companies are pushing off on radio, E911 systems, television, all of that's changing with higher frequency content equipment. Antennas are changing, transmission frequencies are changing, everything's changing around us. And people have been basically ignoring grounding, including, and this is one of our big worries, is they haven't done well enough in terms of even maintaining what they have. A lot of what we find is just, it's been ignored for too long. And we have corrosion, we have damage, we have so much happening that the culture of the industry doesn't right now recognize it's time. Once in a while you gotta go back and check. Many of our peers in this industry are just not following up on their 10-year-old, 20-year-old, 50-year-old grounding systems. And
John,
what that means is two things. It's become obsolete from the changes in the technology, and it's become dangerous from corrosion. Tom, you were saying?
Yeah, I've got your slides up now. Hopefully, you can see. I've got screen sharing up.
I can't. I will not be able to see them, but
Right.
let's move over to the one with that pretty picture of the weeping patent ground rod, if you would. Just to give you a quick sense of how slow that industry has changed. If you go back to 1729, that's when poor Stephen Gray in England was doing experiments like a lot of other science people with the British noble science, all things, everybody does everything from science to hunting to politics, etc. That era. And he was doing experiments with static electricity across the ropes, wet ropes made of hemp and cotton and such. And he kept having trouble with it, and he was wondering where the energy was going, and he finally realized these metal brackets he was using were causing problems. And so it came that in England they discovered that metal carries electricity just as well as, if not better than, cotton and hemp ropes. So that was sort of the beginning of grounding at that moment, as best I can tell on record. And in the 1800s, a guy named Steinheil replaced telegraph return wires with a ground wire and found efficiencies that way and ways he could handle telegraph systems. He made it more complex, but it helped with issues they were having then. And around 1913 was the first example I can see, and now, and this is in US patent literature, of putting salts, Epsom salts and such around a ground rod to help the soil be more conductive. That was the first recognition that the soil was truly part of that, the nearby soil was part of that era, or need. 1931, a guy named Byrne created and patented, in the US Patent Office at least, he patented what is essentially a chem rod. So the first chem rods. So the chem rods are about 90 years old. That surprised me. And then in World War II, when the military was trying to find ways to get rid of copper any place else they could, so not only did Lucky Strike change its packaging to no longer use copper in the green circle, turned it red instead, but UFR was hired to push on putting conductive media in concrete to make a ground, and that was, as far as I could tell, about the last major change in grounding systems, ground rod systems, basically. So it's been slowly changing, and we're trying to add another bullet to that someday, or maybe we'll succeed in getting it accepted enough that what we're doing will make it to a bullet level. Next slide, Tom.
You're up.
Facility grounding sensitivities. I think you're more aware than I am of what you faced in this industry, of all the updates and upgrades in your buildings, your facilities, all the electronics coming at you. The soil in much of the US especially has major issues with being sufficiently conductive for grounding, proper grounding. And you've been relying on that system, and it's treated you well, but you've gotten kind of used to a certain level of lightning damage that is cumulative over time from the power systems coming in, just eating away at your electronics. I used to deal with making high power laser diodes, and it didn't take that much to destroy a die, down inside that chip. In my case, we would blow off the facet for a laser diode's front layer, and all of a sudden it was no longer a laser, it was just sitting there getting hot. So it doesn't take a lot of cumulative. I mean, cumulative can do just as much damage as one big one. You just don't see it happening as readily. It works, and then one day it quits, and you don't know what the assignable cause was. But you do have some clues. If you have continuing damage and cost related to damage from lightning, or the power system, your power lines throwing in faults. If you have systems that have higher electrical noise than you think they should, or over time as they age, you get background noise in your electronics, and even the safety side of it. Some of these don't even go reported, where you get a little bit of a shock down in your control room, and you say, yeah, someday I need to go track that down. Those are clues that your you're harboring some concerns. So I'd like to go to a few photos here of some concerns that we've been seeing highlighted. Let's see, the first one is poor contact. Is that one up, Tom?
Yes, yes.
Okay, the two on the left are basically to point out that what you've relied on and you've been able to rely on is a lot of things going into one small ground wire.
Excuse me, Tom.
Photos.
Tom,
Yeah.
hold your control key and press the plus key on the right side of your keyboard.
Okay.
Control key and then press the plus.
Yeah. Nothing's happening.
Oh. Okay. Any PowerPoint guru here? How to change the size of this real quick?
This is a PDF file that I'm showing.
Yeah, it's a PDF file.
Oh,
Sorry.
then Control plus should have done it. Sorry for the interruption, guys.
So you're getting a small version of the image?
We're seeing 2 pages at once.
Oh, that's unfortunate. Hopefully we can get through it, and we'll make sure a version of this is available, this content. We can't do exactly the NAB version, but we'll make sure we'll get you a copy of something that has the basics of this.
I can put the publisher version up if you wish. I mean the PowerPoint version up if you wish.
My only concern about that is NAB might be a little antsy about us using their what they consider their content now.
This is better now.
Okay.
So I'd rather give in about 6-7 days. I'd rather shoot up a better version tuned to this audience,
That would be fine. We'd appreciate that.
and one that won't get anybody in Dutch. Okay, well, back to the slides for a second. This one has 3 images on it, and you guys see more of these than we do. We're seeing a lot along, but you every day see these things. But the concern is some of your peers are not going back and fixing some of them. The upper right one is an obvious mechanical ground that's been there far too long and uncared for. The other 2 are basically indicative of the trust we put into a relatively small ground wire to handle something from any direction, not realizing that in a case of something like lightning, it jumps from system to system. So a lot of lightning has to go down that wire, and it may come in from multiple directions. So these are concerns that we find, and we find often that single wire coming off, heading to the ground is more useful as a fuse, except when you have that, all that energy that should have gone down the ground is now going right back into your building. And you could avoid that by paying more attention to your grounding and being a bit more paranoid about it. And maybe some of those expensive lightning related issues would not surface. Let's go to the next slide. When Tom's out and about auditing facilities for what we can do, these are not uncommon. Tom, you're about to say something?
No, just your slide is up.
Okay, so you've got mechanical on the left. You've got what could very well be paint in the way of current flow in the middle. And the right one is the one that puzzled me. And I had to talk for a while with our retired Tennessee State electrical inspector partner on that one. So you see a nice heavy duty cable with a nice curl in it along this telephone pole or power pole. And I understand why at the curved area that gets hotter. It's a restriction. Any kink, any curve is going to have lower or higher resistance than the straight line version, but not a huge amount typically, but this is bent. And then he pointed out that the reason that one was so bad and why it charged so badly right in that curl, even though it's such a large piece, was the blasted thing sitting there flush against a giant insulator. That hunk of wood is allowing no energy to go away. So that's why that particular curved section of conductor, when it got hot, just couldn't handle the load and melted its sheathing. So that was a subtle one.
Yeah, adding on to that, John, that particular wire is at a 911 facility in Mobile, Alabama. That is the ground wire coming off the meter base. It is not directly in the sun, that's facing north. So it was not a matter of sun hitting that curve repeatedly. This is at the end of a 1 mile long branch circuit. So this is the end of the line for any fault that's coming in on commercial power. And that particular site was being shut down every 2 to 3 days by faults on commercial power. We fixed that grounding right there, and they've not been shut down in over a year and a half.
So it's kind of nice what a subtle little concern like that can illuminate. All right, let's pop to the next slide. I'm hoping that you're like shifting in your seats when you look at some of these and getting a little nervous. The left one is obviously a concern because there's so few real contact points in that connection. And you're going from copper to steel, and corroded steel no less. I like the idea. They did really good for parallels, tight, but that could be a lot better. It just makes you nervous a bit, especially if it happens to be that the energy is coming in through the copper, heading to the left of the picture, and is expected to go right in the picture into the ground. Depends on how that orientation really is. But electromagnetic field doesn't want to turn around if you can avoid it. And it sure as heck doesn't want to jump from material to a different material, especially when it's corroded and just a bunch of line contacts of that nice wound copper wire against that shaped rod. That's a subtle one as well, but it's kind of scary over time. The one on the right is a ground wire using a fence post that's painted, most of it. It's not a high conductivity fence post. It's just a basic steel post, and it's buried into soil that is, at least to some degree, there's a lot of concrete right in it and around it. That's not an ideal situation. But Tom, I think this one was a tower where there were three of these, three ground leads from the tower legs went to the setup.
Yeah, this was a television tower, and this was the one in Richmond.
Okay.
There were three of these type grounding is 900 foot tall, four-legged self-supporter. And that was the only ground on the tower. That was it. And so what would happen is lightning would strike the tower. It would not go through these grounds. It would then air gap over to the air conditioning units on the top of the studio building next door, which were also not grounded independently. And at that point, the entire neutral of the studio was infected, and it would fry equipment on a regular basis. Again, we replaced all this with a much better grounding system, and now they are taking repeated hits and not having any damage. So it's just a matter of looking carefully at what your grounding actually is and fixing it accordingly.
Even as simplistically as thinking, if I were current coming from the power plant and it was surprisingly large, where would I go? How would I behave? Would I jump to another tower? Is this wire going to handle it? And then thinking about what gets hit with lightning. In this case, you have to concern yourself with the static on that much surface area of tower going through three of these wires. Is that sufficient? Okay, and if we have a lightning strike or another event at that same time while that's being blown, oddly, a lightning strike during a windy day, who would have thought? Is that going to handle it? In our case, in this case, we fixed that. Let's go to the next slide. This is the heebie-jeebie slide, the one that makes you wonder, wow, how long is that there? I hope that was a temporary installation, but when you look up at a tower and you see a nice band of something shiny, hopefully conductive, and some leads running from it, ground leads, and then you walk around a little different angle and you see it's held up there with not much of nothing, just hose clamps. That just makes us nervous. This may have been a setup where it was temporarily set up for somebody to do an experiment. I don't understand that, but I hope to goodness that that's not still there. But that's the kind of thing that you see, and when you're not looking at it in the moment, when you're looking at it in an audit perspective, you just tap your forehead and go, I think we're going to fix that today.
This is at an 1,800 foot tall television tower in Louisiana. There was no other grounding connected to this tower. That was it.
Oh, man. So I think you're getting the point. Next slide, please.
Okay.
Now we're going to shift gears a little bit from pretty pictures of bad situations and talk for a moment about measurements and measurement practices. What we're finding is a large number of power poles, telephone poles that are grounded to very bad soil. And this, we've got dozens of pictures like the one on the left. This is obvious to somebody who has a clamp on ammeter and goes and actually checks. Something's awry. In a simple system like, you know, a ground wire coming from a power pole. What's more subtle is when you have someone come back and give you the data on all the resistance measurements they made around their facility. And the picture on the right is, there were 26, I only put a few of them here, and they all were 17 point something something. It's kind of silly to use that many decimal places. Maybe it makes somebody in the company feel better that you got a lot of quality of data here. No, that's just noise over there. But the point being, look at all of those. Anything suspicious about that? Yeah, they're just too close. This is the kind of a clue you get that something's awry here. Tom, you're the one that got this in and sussed it out.
Yeah, this was at a site that had taken a lightning strike recently. And this was a report that the engineers that did their grounding put together 3 years ago. And I got to the third site that they reported here, the interior main panel, and they were all 17s. And I said, well, that's not right. Well, then I found out that what they were doing was running around the inside and outside of the facility with a clamp-on meter. I'm sorry, not a clamp-on. They were using a fall potential meter. All the numbers are the same because all the grounds went to a ring. All they were doing was measuring the effectiveness of and the continuity to the ring. They were not measuring resistance to ground at all of any consequence, even though it was a fall of potential. The differences were just different points of contact. It was not a good reading, and 17 ohms is not something you want to write home about anyway. We can also talk about it. Maybe John, you're going to talk about this. Using clamp-on meters and even fall potential meters is questionable because you're asking a 6-volt or 12-volt battery to emulate lightning. That's just not going to happen. And when you have a lightning strike, it's going to have a whole different behavior inside a grounding system than what a 12-volt battery can put into it. That's just a simple way to put it. These are good numbers to check the relative strength, the relative health of your grounding system, but they are not absolute numbers and should not be treated as such.
That gets to regulations and standards, basically. The people who are putting together regulations and standards are limited by what they can expect the people running the test to have.
Are you there, John? Did we lose you? My goodness.
There we go. I'm back. I think I should be back. It's a very strange setup I'm using here on Zoom, but 25 ohms resistance to ground is a National Electric Code, in part because that's easy to measure with the equipment that you should be able to afford and have in the field. Though generally they don't even have a clamp-on ammeter to do that in the residential market. At least they just put 2 rods in and go from there and pray. But I know that from our experience that very often we're seeing numbers like 380 ohms after there's 2 ground rods in there. And so you can't trust totally what you were given when you bought your grounding system to have been done properly. And you can't trust totally that 25 ohm number because you're not getting it if they're just putting in rods. So I just want you to be aware that there's some clues you can get, like a suspiciously long list of one resistance value that doesn't make sense. Someone's not using their fall potential meter properly. Let's go to the next slide.
I had a question on the clamp-on
Yes.
meter.
Yes, please.
So it appears to me that is acting as a transformer with a 1-turn primary, say, and then the meters doing the secondary, and then determining the impedance of the loop that is passing through the core. So it seems like I'm guessing that this photo is a ground wire on a pole, which is then going up to a wire to another pole, and then coming down to another ground rod. So what we're seeing, I think, is the resistance between those two ground rods, right?
Yes and no. What we're trying to find out here is, how do I explain this?
This is going to a transformer.
Yeah, you're okay. I'm going to say yes. That's effectively correct. We're looking at the resistance through Earth, the impedance through Earth, which then gets back into the neutral system of the electric system and ends up getting to the transformer. It is a loop indeed, but it is measured through the Earth. The ground rod then pushes this signal through the Earth. It gets picked up by another ground rod and back into the system. It's measuring that distance. It's how, and what we're trying to measure with this clamp-on meter in this case is how bad is the soil around this particular ground rod, and is it going to be able to dissipate any charge that's put into that wire? In this case,
we're measuring the efficiency of the interface with the soil and dissipation into the soil at this point. So if you
I'm just trying to look at the electrical circuit that if we assume this is a pole and there's a neutral wire running between poles with a ground rod at each pole, then the ground resistances of all those other ground rods are in parallel and ideally lower. So this is this particular rod would be the major contributor to what we're reading. But you know, if there's only one other rod in the loop, we don't really know which one's bad.
No, and it's not really important to know which one's bad. It's just to tell you that when you get a reading of 600 ohms, you do not have an effective ground.
Okay, thank you.
Oh, I would go one step further than that. I think we're all overthinking it a bit. The energy dissipation into the ground at this location is driving the dominant portion of that measurement. Its contributions elsewhere are real, but this one, if you put a second rod by it, then that ground system in that location, if you split that into two rods, that would go to right at half that 600 ohms. They'd go right at 300 ohms. So to some large degree, we're measuring the efficacy of inserting energy into the soil. And that's a measure of, to some degree, of the soil itself. But it's what you're worried about at this point. If that number is higher, then the amount of energy that makes it into the ground circuit, if you will, that's dissipated into the earth is affected dramatically by the quality of that ground. You know, this is coming from a pole with a transformer right up there, so it's in that near area, and that's what's at risk at this particular pole. And basically most of the poles, if not all of them that I see, have got a ground that is associated with the transformer. And we're looking at it and saying, if it's 600, that's about half. You've got a huge amount of energy that can reflect back up into the electrical system. It's not being dissipated. And if you put in a better ground there, then I can get rid of it gracefully before it gets to the TV tower, before it gets to the E911 center.
Or the transmitter.
That's what that number means to us. That number means to us how well I am protected by the power company's grounding system. And it is to some degree cumulative along the other poles, but each one of those has had an opportunity to dissipate some of the energy that came from whatever fault. And if this is the one nearest my facility that I'm worried about, I'm going to be very worried that pole's ground is not contributing much of anything to my safety.
What I'm finding in my field surveys, folks, is I check especially if we're at the end of a branch line, which is really, really dangerous for any kind of transmitter facility. Utility grounding generally is awful. They put one ground rod in the ground and go away. They say we're done. Sometimes they do what's called a butt ramp, where they just take number 6 copper wire and wrap it around the bottom of the pole and bury the pole. These do not give good dissipation numbers. When you're at the end of a branch line, sometimes, as I mentioned earlier, a mile long or half a mile long, any fault that happens near, any lightning strike as an example, that happens near that line will carry, that line will carry some of that fault towards, or go in either direction. But if you're at the end of the branch line, you're the big catcher's mitt at the end of the branch line. We're finding in my experience that over 60% of the damage that happens at broadcast facilities from lightning is not from a tower strike or a building strike, it's from referred fault on the power lines. Another big thing to consider is, well, a lot of people say surge suppressors will catch that. Even the fastest surge suppressors have trouble with very, very high frequencies that are found in lightning. But more importantly, in the case of utility poles, there's a neutral line. Often it's the wire on the very top of the poles, the highest wire there. That neutral line has a free pass basically into your facility. All it's got to protect it is one ground rod, typically at the serving transformer or at the meter base, and that's it. Surge suppressors very, very rarely have any protection on the neutral line. At that point, you've got a lot of trouble inside your facility. So we focus on, especially in this situation, on the commercial power supply, we focus on making sure that's extremely well grounded before it gets into your building. And that intercepts a lot of trouble. And that's probably one of the reasons we're having the success we're having. Next slide, John.
Yeah, let's
Also,
go ahead.
also surge suppressors shunt to ground. So if you do not have good ground, they're not going to do much.
That's exactly right. In fact, they become sacrificial at that point. And that's just a giant expense that you really shouldn't have to incur. If you had better grounding, you wouldn't have a burned up surge suppressor. I've got the next slide up, John.
Okay, this essentially, I think you all know there's a lot of stuff coming at you with a lot of acronyms. We can skip that slide. But I do want to point out, this is what's also new and changed slide. I do want to point out that we've been learning a lot over the years about the environment around towers. We've been learning about lightning, ground rods, and by we, I mean society, science in general. But what hasn't made it into our consciousness as much is all the data that's been coming around for the last 50 years on lightning and its broadbandedness. A lot of times I see assumptions made that lightning is pretty well all DC. There's a big chunk of it down in the DC or close to DC, and that's what people first order will think about, but they forget when they see that chart of the energy dissipation frequency content that it does taper off going to the right, and there is this beautiful 60 megahertz spike that shows up even more pronounced when it's a cloud to cloud, but it never really gets to the bottom. So you have to remember there's a lot of energy in those higher frequencies out there. If you look at Fourier transforms, the frequencies it takes to create a very sharp vertical spike, a delta, a hockey stick, that's high frequency content it takes to create that. So I am asserting that a huge amount of the high frequency content is in that initial rise time, and then it settles out more towards the lower frequencies later in the pulse. So I've been working from a model that says that a lightning event or a sharp pulse event of any type, that the decisions about where the energy is going to go first, where it's going to jump, the direction is going to change as lightning jogs back and forth in different directions, those are made in the high frequency regime. So that's why I worry so much personally about the solid copper conductor. At the beginning of that pulse, I think it's doing you a disservice. You're only getting that outer skin of it. The high frequency component travels on the outer surface, which is why you have so many thin wires with lots of surface area for doing your high frequency, your tweeters on your stereo. So that's the understanding of those areas has been driving some of what we've been chasing. And the proof in the pudding thus far that's not a bad assumption is the results we're getting with actually helping facilities take a lightning strike more graciously. So there's still a lot more science and understanding to be achieved, but that's the model I'm working with mostly. is that the high frequency component that is there that we tend to neglect is making, is causing much of the decisions to be made in high frequency thinking as opposed to low frequency thinking about where energy is about to go and how it jumps from point to point during a strike. We're also learning a lot more about just how lousy the soil is in places. You know, we want to put towers out in the field and up on a mountaintop where they work very well, but mountaintops are, you know, just replete with bad soil because they're basically decaying limestone mountains essentially, and that ends up giving us a very poor grounding situation. Pardon me, please. So these are some of the concerns that we deal with and that we know are changing over time. And then Tom mentioned earlier that we're also recognizing that we're seeing more and more of an impact of our standards and our standard equipment, standard measurements use a 9 or a 12 volt battery to simulate lightning, and that's just not helping. You know, it's not designed to simulate lightning, but it's being used to design a system, put together a system that has to handle lightning or a pulse, any kind of a fault. That's just not working as well as you'd think. So we're learning some limitations of what's being done, and that's guiding how we're addressing grounding for important systems. I'd love to just pop to the next slide. Let's see. With a little luck, we can avoid that and a little bit of science. So let's move to away from the exploding balloon.
Yeah,
here's more of what we want to see. And Tom, I want you to address this one because this I would rather see this than an exploding dirigible or balloon of any sort, and death and destruction for that. This is what we're chasing, Tom.
Right. This is WTBR again in Richmond. A security camera took this shot in August of 2021. We completed regrounding this facility in June of 21. I think I've mentioned already, this tower has now been hit 5 times since June of 21, and they have not had any downtime or other than losing one camera motor, which was not connected anywhere to the grounding system. That's the only thing they've lost, but no lost airtime, no transmitter loss, no major electrical loss. They've spent $200 so far, which makes us very happy. Anecdotally, the first strike on this tower happened when I only had 20% of the system in, and I was quite nervous. But I may have told this group the story already. If I have, you can shut me off. But the tower got hit. Everybody, I was inside the studio at the time and in the engineering room right next to the master control room. And of course, everybody was suddenly very scared and they were sniffing for smoke to see what it was going to go up in flames, so to speak. And the intercom cracked alive and the station manager came on and said, "Is everybody up? Are we okay? Are we okay?" And everybody checked in like a NASA launch. Yeah, we're go. Yeah, we're go, 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 go. Everything's good. And the station manager then said, "That's impossible. We've never had that happen before." Well, it was true. We only had 20% of the system in, but it ate a lightning strike. So I was very confident going forward at that point. And then we got this picture from a nearby, I guess it was a ring system. Somebody went through their footage and found this, and they posted it on Facebook, and I grabbed it off of Facebook. But it's obviously a direct strike on our tower, and nothing happened. Like I said, there've been 3 more strikes after this, so a total of 5 and no damage.
Proof is in the pudding, I guess. Yeah, let's pop over to the next slide.
Okay,
If you don't mind.
I've already done that.
Okay, so essentially, at the end of the day, depending on what's the motivation of your facility, there's a lot at stake. It's military, it's mission completeness, but the one that seems to be rising in our awareness, we're finding anecdotal evidence more, is the signal to noise. We're having people that are are complaining about some of their equipment has gotten noisier than they would like. And we'd like to chase down more of that. And that may be the high frequency components, may not. But we do have evidence that profits and uptimes clearly have been affected by just improving the grounding. But what I would beg of you is that you take time to audit your systems and fix what needs fixing, what makes you nervous. Try to make sure that whoever maintains in terms of corrosion, that they actually get out and take the time to do that, because you need to get rid of all that energy on a bad moment. And upgrade your systems whenever you get an opportunity to put in for the budget to do some upgrades. And if it's us, that's great. Otherwise, just add some capacity and keep in mind the frequency content of what you use when you're addressing the updating of your systems, your grounding systems. And that's all the slides. You want to go into questions, or is there another point you want to bring up, Tom?
We'll go for questions, and I've got my whole presentation as well, that if the group wants to hear it, I can do that. And they can hold questions until then, or actually, John, you have to go. So if there are any questions out there on John's talk, I would say go ahead with those right now.
Just to make you jealous, guys, I'm in Hawaii, looking at the ocean, about to go on a little tour. It's still a reasonable time of day here. So,
Good ground conductivity there.
I'm on a rock in the ocean. I don't know, is it?
Actually, Hawaii,
Well, the ocean is.
Yeah,
Oh,
yes.
the ocean, yeah. But this is a bunch of volcanic rock, as far as I can tell.
Hawaii,
Hawaii.
Has terrible grounding everywhere.
I would expect it to be terrible here because Kauai, it's volcanic, but there is a fair amount of topsoil that's helpful with the lush greenery. Oh well, but okay, questions.
I think I talked with you both perhaps at NAB a few years ago, and there was discussion about the impedance transition between the ground conductor and the earth, and looking at reflections coming back from a sudden transition and so on. So and this is especially the case on that rising edge where there's a lot of high frequency content. So I'm wondering if we have a generator and then a transmission line and then say a short at the end, we're going to get a lot of reflection. But if we do several shorter transmission lines with smaller transitions, is there indeed less reflection, or is it just spread out over time?
That's for John.
Yeah, I'm trying to visualize in my head.
I'm just trying to
Go ahead.
imagine what the smooth transition does, because we're still going from a low resistance to a high resistance, as to what it does doing that slowly as opposed to suddenly.
Yeah, well, I think of it a lot as like anti-reflection coatings on your glasses or a telescope or something. I can tune that interface significantly, but once I've gotten it pretty good, the changes are small. Going from the old purple coatings to hardly seeing a coating at all now, it's different from like 98.5% efficiency to 99.2% efficiency. In this case, if I'm working with 3 separate ground rods at a short distance, for example, and I'm counting on the 3 of those to reflect, they'll all reflect based on how good or poor the interface is between that rod and the soil, versus one 3 times the distance away. Clearly I'm getting, is what you're asking about the longitudinal surface of the conductor over 3 times the distance, or is it more about having multitudes of like endpoints? When you're thinking about that, what are you thinking about?
Well, I remember something about, I think it was perhaps a copper conductor, and then some carbon around it to sort of smooth the transition from low impedance to the ground. And
Yes, okay.
The idea there
Now I
was that reduce reflections. And I'm wondering, how much difference does that really make? Because one way or another, you're still going from a low impedance to a high impedance.
Yeah, well, what happens is the third and fourth material in that line. So you go from, say, copper to something that's 70% the reflectance of copper at that frequency. And that would, in one case, would be carbon's one example for that. And then you go to another material that's pretty terrible soil, and that interface is real. The next layer might be much better soil. You know, so there's different, each time you pass materials, that impedance mismatch at that interface is what you're dealing with. But bear in mind, the third and the fourth interface, its reflectance is being dealt with in part by going the upstream the other way. It's now reflecting that same percentage that it reflected earlier, but back downstream. So it's a multiple pass approach. You're peeling off what you can each chance you get an opportunity to, but every time you're at each of the interfaces, you're reflecting back upstream. But that energy from whichever interface you're dealing with is getting absorbed along that length, and that's part of what you're dealing with, is that absorption length along the surface. How much of that energy is dissipating on that outer surface of the conductor into the soil. But the copper to the native soil is what you're trying to defeat. So that's a pretty lousy dissipation point. It's like the core of an optical fiber. It would much rather stay in the core than go out into the glass on the outer part of the fiber out into the world. In this case, the energy would much rather stay in the copper than go out into the soil, no matter how long your conductor is. It's a lousy interface for dissipating. It's better than nothing. So don't put all your.
Speaking of nothing, this is from one of our viewers, Tim Braddock.
Yeah. Yeah. I'm sorry.
There's a ground connection there somewhere?
That's
what am I
the
missing?
point.
Yeah, I don't see one.
Oh, I think it's that cut off copper at the far right.
Oh, you have a picture? I'm sorry, Tom. I don't.
Yeah. Where are we going out to ground here? Can anybody? Tim, can you tell me? Tim's supplied the picture. I guess he can't hear me.
Okay, here we go. I got the picture now.
There I am. So this was a very prominent radio station in Wilmington, Delaware, whose call letters I won't reveal. And this is the first day I walked in. In my mind, the polyphasers should be outdoors with wide copper flat strap going to, in this case, it would have had to be building steel. But I mean, this is a disaster waiting to happen. All of the STLs and the satellite and everything come through this. And I mean, that is definitely not a good example of what to do with a grounding system, but I had to show it because it was hilarious when I walked in.
I agree completely. Where are we going to ground here?
We aren't. That's the problem.
Yeah, I don't see an off ramp.
Right. Number two, polyphasers in my 2A business, polyphasers go outdoors and then they get weatherproofed, and then the copper strap or ground straps go outdoors. This is bringing it in the building. I mean, now you're in the building. Even if you had ground straps on this, now you're in the room. You're literally in the room with the STLs and the computer playout system. It's just, you know, this got fixed real quick.
I'm going to steal that picture if I can.
Yes, please.
I'm just going to be a picture of a picture, but I'm going to put that in my bad grounding file.
I'll send you the file, Tom.
Yeah, go ahead.
Great. What we normally see in this, that's a dandy one.
There you go.
Yeah, send me that one too, Barry. Yeah, this is just, we see this stuff all the time, and it's stunning to us. So that's why we came up with the concept that you'll see or hear about, if I can keep a few of you a little bit longer, in our oh, geez, stop it, Tim, stop it, you're killing me.
That one's not for me, but I've got more.
Well, okay, I'll send you an email and you can send them to me, because
Yeah, no, they're goodies. Empire State Building and World Trade Center.
Oh boy. We've come up with the concept of that we're encouraging our customers and potential customers to do, and that's First of all, audit what you've got, literally audit it. Figure out what's going on in your grounding system. A lot of operators don't even know. They have a facility that was built and the engineers built what was spec'd for them. And that's all they know. They don't know where the grounding is. They don't know what it is. They don't know a thing about it. So audit your system, find out what kind of grounding is there, assess what you've got and what your electronic risk is. We stress the electronics. We're all electronic now. We're all solid state. Everybody's got everything solid state, but the grounding that was used was designed for analog systems. Absolutely just for analog systems. Tim, you mentioned about copper strap. We see that an awful lot. And it's a big, wide copper strap, maybe sometimes 6 inches wide. And they terminate it into a number 6 wire. Well, what's going to happen to all those?
Or they wrap it around the ground, or they wrap the copper around a ground pipe, a copper ground rod, and then try and solder it or thermo weld it. And you know, my 2A and cellular background has seen. I'll send you some real nightmare pictures. I mean, just how the hell did this ever work? Pictures.
Yeah, Tom LaBarge run together at groundlinks.com. There you go. Love to see them. It's scary. I think you've made reference to R56, and R56 does also another good point. I'm sorry, I'm jumping around. Another really good point was made. Once a fault is inside the building, all bets are off. What we do is keep it outside the building at all costs. Any way we can keep it outside, we're happy. But R56 is a great document for inside the building, but when they go to the business end of grounding, we have some concerns with the way they promote. And that's the angle we play. We prefer to supplement R56 or anybody else's documents. We'll always add on to it. Any ground is a good ground. We like to think our ground is a better ground, but we just add on. We don't ever take anything out. So I'd like to hear R56, but I like to add on to it at the end. I got kind of out of hand there. Sorry. He got me excited with those pictures.
Another quick comment. What about building steel? Like in New York City, where we have radio stations in steel buildings. And I had one instance where I had a 60-foot tower on top of the building, and it was not connected to anything but 3 bolts through the base plate into maybe an I-beam. And there was nothing else on the tower, and lightning stripped the lawn chairs right off the tower. But building steel, you know, what's your comments on building steel?
Well, steel is just not a great conductor to begin with, which bothers me. But just and I'm not an engineer. That's why I rely on Mr. Belk to take care of the engineering concepts. But what I think about is just practically where you've got to get rid of the energy. It's got to go somewhere. You can't destroy energy. It's got to go somewhere. It'll turn to heat. Well, yeah, that's changing form. But if you're just pumping into building steel, are you turning it into a giant radiator? Is that what you're trying to do?
On top of a building, though, it doesn't seem like you have much choice. You're not going to run a 1,000-foot copper strap.
Or 500 MCM all the way down to a bunch of grounding devices somehow buried in the rock of Manhattan.
No,
I have a feeling the structural steel would have lower conductance than that, or lower resistance than that.
You have some of the older buildings too, like I had in New York City, where, you know, does steel really attach to other steel? I mean, even the Empire State Building, where, you know, we had monster runs of all kinds of stuff in there. You know, we had to run extensive grounds within our own suite and then tie that to the 4 points in the corner of the building to building steel. And it's still, you know, we still didn't get the best measurements, but like Harold said, when you're up in a building, what do you do?
Yeah, I don't have an answer on that, and I have no.
I may.
Okay, go.
I'm sitting here thinking of it in the anti-reflection coating world, and you're jumping precipitously from copper wire to half that electrical conductivity steel. And I think you could benefit in the efficiency of getting the energy into the steel by altering that interface with multiple layers of properly chosen material. And that might be actually doable. You know, you'd be more effectively inserting the energy into the steel as opposed to sending it back up the copper wire. Interesting thought. some pondering to be done there, folks.
Would there be much dissipation in that interface?
The interface would not do much. All you're doing is you're improving the transmission part of it. You would be putting more of the energy into the steel at the earliest opportunity.
That's interesting.
That would
I had another question of on these sites where there's not been sufficient grounding and lightning has damaged stuff. Do you see a change in the earth around the ground rod? Has that interface been heated?
I don't ever excavate anybody's grounds, so I don't know what's going on at that point. All I do is add. We have exhumed our system after they've been hit, and we find no damage and no changes at all.
Yeah, I wonder. It seems like if there's some resistance there, and then you're going to get heating in the immediate area. I don't. Maybe it's farther down the rod. I don't know.
Well, just think about it. There's some artists who take advantage of lightning rods in buckets of, in big bins of sand in areas where they try to get lightning to hit, and they're making glass sculptures doing that.
True story.
So there's enough heat in there to melt sand into glass, dissipate into really terrible soil. Well, we're looking at some pretty bad soil here. Maybe not as bad as just pure beach sand. Oh, never mind. Florida exists. So I think the answer is yes. There is local heating, as well as I've seen personally where lightning lifted all the leaves running between the tree base and the transformer, made it look like a gopher ran underneath those leaves for about 200 feet in my own yard, by the way. So there's a lot of energy being dissipated there, and some of it's going to heat. And according to the glass artists, some of it's enough to heat glass, make glass out of sand.
I think the secret with our particular arrangement, which some of you are aware of and some are not, is that we have such a tremendous number of dissipation points. We're able to manage the heat buildup so that it's not really even there, and so we end up with a system that's not sacrificial in any regard and can take multiple hits and still work. So we're not seeing any change around ours in particular. That's a function of the surface area that we have and the millions of dissipation points we have in each of our electrodes. Shall I move on to mine, or do we have more questions?
Well, I think we should probably move along here, Tom. We're at an hour, so let's get into this part and see where we go.
I'll go through this as quickly as I can because we have used up an hour, and I'm appreciative of that, but want to add a couple more points if we can. So this was a presentation I gave to a group of loss prevention people that are closely involved in the public safety world. They are the largest insurer of public safety facilities across the country, and they are engaging us to help them redesign their audit procedures. I've changed it a little bit so that it applies equally well to broadcasters. And what we're trying to do here is just encourage you to start thinking about grounding a little bit differently. So without further ado, I'll start changing the slides with their fancy effects. We already went through this on John's presentation. Traditional grounding's been around forever, almost forever. And the last major change was indeed Herbert Ufer in 1942, who had to find a different way to ground because there wasn't any copper left. We were making bullets with it instead. So that I won't repeat that. Although on the second bullet point on the screen says that traditional electrical grounding is analog based. It's designed for grounding relatively low voltage and low frequency currents. And of course, you go back to Franklin and Faraday and Volta and Morse and Edison. That was the inspiration for what's out there. Common grounding standards, you all know them. You've seen R56, there it is right there, NFPA 70 and NFPA 780. And the IEEE, of course. Oh, we were talking about New York City, and I forgot to bring this up. Tom Silliman, whom I consider a friend, and maybe many of you know him, at ERI in Chandler, Indiana. Tom's, 74, and he still climbs towers. And he's done a lot of work on the Empire State Building. So he might be a good guy to find out about how they can improve grounding up there. Anyway, back to the presentation. We've got a lot of guidelines, but again, they all rely on the use of ground rods or chemically enhanced rods. The gentleman in North Carolina, I can't say your name, at the observatory, are you still here? Barry, help me out. Who was the gentleman in North Carolina on the pistol?
Yes, that would be me.
There you are. There, Lamar, there we go. You said you have a lot of chem rods in place there.
Yeah, they're old, but they're here.
Does anybody maintain them?
They have not been maintained that I know of.
I've never seen a single chem rod, deployed chem rod in all my travels. I've never seen a maintained chem rod. In fact, many of them have copper caps on a copper tube, and the insertion of salts has caused the cap to basically weld itself to the pipe. So you can't even access them to add salts to them. Anyway, chemically enhanced ground rods are common. Ground rods are all out there. They're all very standard. They're all specified in these documents. What I say here in the yellow print, I'm going as fast as I can here. Electronic and digital devices have indeed changed the world, but grounding to protect these devices hasn't changed, and that's disappointing. We need to start to look at grounding a little bit different. What we have out there is really, it's obsolete. Some of the same graphics here as John's presentation, as it turns out. We don't pay attention to grounding. We don't know what's out there. When we build something, we make sure it's in spec, but again, the technology hasn't changed, and it needs to, because electronics are far more sensitive than what traditional grounding was designed for. Because of this, we're having many more equipment losses that are very expensive. If you blow up a transmitter, you can't very well call up Joe's transmitter shop and say, give me a new transmitter. It takes a little bit longer than that. You don't want to take that kind of downtime. I do a lot of work in the 911 world. They don't have the luxury of having that downtime. They've got to be on air. They are mission critical. So they've been after us quite a bit, and we've been very helpful for them, as it turns out. So the elements of obsolescence. It's a DC event, but it has some AC characteristics and a wide range of frequencies. You heard John talking about that. We're relying on a dated understanding of fault events. Copper, as it turns out, doesn't do very well when you get above 60 megahertz. You got copper strap, that is helpful, but eventually that starts to tail off as far as conductivity goes, or dissipation ability. You heard me talk earlier in John's presentation about commercial power lines. There are a tremendous number of damage events occur simply because of faults on power lines, and we're not protected against those. I think in the Blue Ridge area, which is mountainous, I think the average ground, I've checked about 100 power poles here from a particular EMC, and we average around 350 ohms. That's not a very good ground, and if there's a fault on that line, it's going to come to your house or your business, and it's going to cause a problem. Another element of obsolescence is the measure wrong. We've already talked about this a little bit. You can't simulate a lightning level event. However, using these meters is a very good thing to do to get a basic feel in relative terms. How is your grounding in place? Is it working well? Is it connected? Is it designed halfway well? Yes. Does that tell you how well it's going to handle a lightning strike? No, it does not, unfortunately. Too often we treat these readings as absolute numbers. They vary hourly, they vary by the day, they vary how well you have the alligator clip on. It's a huge problem. On the right-hand side here, there's a picture, hopefully you all can see it, of a engineer, a stamped engineer, who was evaluating a 911 site in Florida. And he happily reported that all of his grounding that he put in had a resistance to ground of less than 0.08 ohms. In this case, it's 0.05 ohms. Well, that's noise, and it's not even an issue. turns out when we looked into the methodology this particular stamp engineer used, all he was doing was checking the continuity of the grounding ring. So we had some copper in place, it was all hooked up, but it said nothing about the grounding ability. So we got to make sure that we measure things correctly. That was referred to in John's presentation as well. Here on the right, you can see a picture of a test loop in a pit that I happen to spot, and the test loop, as you can see, is connected onto the ground ring, not to the grounding device itself. Any test done on this will do nothing more than connect or than check the continuity of the ground loop of the ground ring, and will tell you nothing about the ability to dissipate a surge. Surge suppressors, we talked about that already. And yes, they do dissipate to ground. If the ground is crappy, all they're going to do is burn out. The cost of obsolescence in grounding, data centers, we found a lot of data out there. $10,000 per minute of infrastructure downtime is not an unreasonable number. For insurance providers, they're spending huge amounts of money now. Florida is over $150 million a year in claims just for lightning, not fire related to it, just for lightning damage to equipment. That's one state and $150 million a year. That's pretty serious stuff. Europe is even worse, and that's a long story, but it has to do with the fact that they use 220 volt distribution, and their service transformers are many times 300 meters away, and there's no suitable grounding at the various structures that are being served. The result is damage in the structures. A fault never makes it to ground. We can talk about that another time if anybody wants to. Losses that we're having that are triggered by preventable events just aren't acceptable, and better grounding can take care of that. Like John wrote, what needs to change? Let's do audits. Let's find out what we've got. Grounding technology hasn't really changed in years. And the result of that is we assume that if we have grounding in place, it's fine. But our equipment has become more sensitive. We have not upped the game, shall we say, with respect to grounding. We need to think about that. And there is better grounding out there right now. And sorry about that interruption. We need to view grounding as a dynamic and necessary protection. All of our assets are mission critical when you get right down to it. If you're in the broadcast business, it's mission critical. We're not paying enough attention to it. We need to have grounding that is able to take care of fully mitigate an entire fault event. A lot of traditional grounding doesn't do that very well. I'm going as fast as I can, and maybe I'm going too fast. You've seen the picture on the right already. That's the facility in Richmond that we've had some success at. When it comes to broadcasting, your grounding is your first line of defense against electronic equipment damage and loss. We highly encourage you to, as John was saying, take a look carefully at what you got. It may be up to spec, but spec is deficient these days. I can also make this presentation available to anybody. Maybe I should do that through Barry. Barry, if you want to, I can email this to you and you can distribute it to anybody that wants, if that's of interest at all.
Sure.
I'm going through awfully fast, and I apologize for that, but I don't want to waste any more time with anybody. So, John made reference to, and I talked about R56 at one point. I've had a few discussions with some R56 engineers, shall we say, and they want everything everywhere that's metal grounded somehow. At one point on a job, somebody said, I need to have 27 stingers added to this 80-foot piece of wire because anything that's metal around here, I'm going to attach to grounding. I said, why? He didn't know the answer. He just said, because the spec says I have to do that. Maybe one of you can explain to me why he wanted so many grounding leads to anything metal around. I see grounding as just get it in the ground and get it going. Maybe I'm missing a point there, but Instead, as I say in the yellow here, we should just concentrate on preventing the entry of fault currents into a mission critical facility, regardless of the source. Just get it gone. We spend an awful lot of time on connecting every wire we can think of to a bus bar and then trying to cram it down a number 6 wire. I don't get that. Earlier in the presentation, I talked about the neutral side. I got it as a decolor down at the bottom of this slide. Maybe you can see it. Neutral side grounding is extremely deficient, and it's a free pass into your facility. Watch that very, very carefully to make sure you've got your neutral wire has access to very, very good grounding. Nobody pays attention to that. R56 doesn't pay attention to that sufficiently, in our opinion, and power companies couldn't care less. So if we should try to eliminate off-air events and cut costs, we can do that by looking at the importance of proper broadband grounding. John talked an awful lot about frequency issues. Traditional grounding doesn't even consider that, unfortunately. Inspect the system and do system audits, find out what new knowledge can help out your grounding system, identify your weaknesses, and take a look at enhancing or supplementing the grounding you've got. Highly encourage everybody to rethink the entire process of electrical grounding. Technology has changed, but grounding hasn't. Need to bring that game up. For broadcasters, uptime is essential. It's also essential for 911, which is what this was prepared for primarily. Treat grounding as your first line of defense. It will pay off very, very quickly. If any of the CFOs are out there, or if you interface with CFOs, you can explain it to them. They'll save them money. They'll get it real fast. That's pretty much it. There was one addendum here that I made reference to. These are the 3 steps we're really pushing now. Audit what you've got, assess your electronic risk, and then augment. Don't ever take out a ground. Any ground's a good ground. Add to it, and expand the abilities of your grounding to handle all levels of intensity and frequency. And that will save you a lot of money down the road, and a lot of headaches, and you won't get those late night phone calls either. Okay, I did that awfully fast, and I apologize if it wasn't clear. Ask questions, please.
Sure, appreciate that, Tom. And I know that on your website, you've got several articles that are already posted, and you're going to bring some things to us to bring it a little closer as to why and how to have an effective ground. So anyone have questions, please unmute, talk to us, raise your hand, jump up and down, send us an email. Well, something like that.
So I had a question on AM station grounding with the large buried radial field. Does that provide adequate protection against lightning if that's used as the ground? Seems like it's a lot of surface area.
It does. I'd have to see the exact layout of it and see what we're trying to protect. If there's no exposure to your structures and to your transmitters at that point, if it's entirely independent, which many of them are, you can dissipate in the ground all you want. We're just trying to prevent damage to your equipment. I'm not that familiar with the AM world. What kind of losses are AM stations seeing? Is it transmitter issues? Is it lights on the towers? It's all going to depend on what is being damaged to answer that question.
Tom, one of the things you talk about or haven't talked about, I don't know, one of the things broadcasters often talk about is being forced to choose between open and closed delta systems. And as your focus today on commercial power, maybe you could talk for just a couple of moments about the dangers that you've seen there.
Well, again, if you treat an open or closed delta, if it is traditional grounding, it's by definition it has limitations. And I'm not sure that any type of delta arrangement is better than another. Any ground is a good ground, to the extent that it can perform. I would much rather put in a more robust grounding system than just relying on a traditional delta design. It's very, very common. There's all kinds of disagreement on how many ground rods you need to have and how close they can be and how far away they should be and the sphere of influence issues. Well, let me change gears slightly. How many have seen the little drawing that shows you about sphere of influence around ground rods, and they have to be X number of feet away? How many people have seen that? All right, I see hands going up. I was able to prove very, very quickly that sphere of influence argument really is only electromagnetic fields, is not dissipation of current. When it comes to resistivity of a grounding system, the reason for that is the dissipation from a ground rod occurs only at the tip of the ground rod. It does not occur down the length of the ground rod in any significant amount. And the way I was able to show that was by simply hooking up the fall potential meter to a ground rod and taking a measurement every 6 inches. I did this in 4 US states, got the same results everywhere. The theory is the deeper the ground rod goes in, the lower your resistance to ground should be. It's not necessarily true. In the case where I did the first test right here in Blue Ridge, Georgia, I got lowering resistance for the first 20 inches, and then suddenly the resistance started to go up very quickly. Obviously, I was getting into different soil. Well, why am I getting that reading if it's just the tip? If the entire rod is dissipating current, I shouldn't get such a big spike in the resistance by going into the ground deeper. Well, at 43.5 inches, I hit rock. Resistance went to 2,800 ohms. And it happened right at the time I hit rock. That told me that all dissipation in that system was being done at the tip of the ground rod. I tried it in soils in 3 other states and got the similar results. It all depends on where the tip of the ground rod is. It has nothing to do with the sides of the ground rod. And John talked a little bit about that when he was talking about reflectivity. The difference in resistivity, not necessarily resistance, but resistivity of copper versus any native soil is on the order of 1 trillion times. Current will tend to stay in copper as long as it can until it gets kicked off. That happens to be at the end of the ground rod, not along the sides. So when we get back to deltas, open and closed deltas, if we're talking about just ground rods, I prefer to design a much more effective system, and don't pay a whole lot of respect, if you will, to the deltas. Does that help at all, Barry?
Yep, that addresses the issue, and we want to address it further. But I think you've answered the basic question for most folks.
I've talked too much. Any other questions?
Just a comment from something that happened to me a number of years ago. Harold brought up the idea of ground radials from AMs. AMs were my bread and butter for a long time and still are to a degree, but directional AMs in particular. And we made the mistake one time when installing a new transmitter. This tells you how long ago it was. It was a DX25 Harris. And so that's been a number of years back. In fact, it was September 11th, 2001 was when I was supposed to do the final install on that transmitter. And the electrical inspector got really, really upset when I called the radial system a ground. And he wanted me to put an electrode at the end of every radial wire. I kid you not. Yeah, Barry, I saw that expression. So, and this was a 4-tower inline with about, somewhere around 900 radial wires, all of them number 6 solid copper, all properly brazed, not CAD welded, unfortunately, but brazed. He got real upset about brazing versus CAD welding. CAD welding is an appropriate bonding technique. Brazing is not. in the electrical world. So I changed my terminology and I called it an RF counterpoise, and he left me alone. So that's my anecdote for the day.
That was slick, LaBarge. That was slick. There's more than one way to skin a cat, apparently.
That is interesting in that there is a lot of surface area, but it also is not very, very deep.
I'm not a radio engineer. I admit that fully. As I understand it, though, the radio system in an AM tower, that's half the antenna. Is that correct?
Yeah, the tower is the antenna, and the counterpoise provides a reflection of the antenna and the ground.
Okay, all right. That kind of makes sense. What kind of damage have you seen in the AM world from lightning?
I have seen melted strap, 6-inch strap melted in two like fuses. It's pretty rough.
But damage to equipment.
Damage to equipment. I have seen holes blown in the side of 4CX 35,000 tubes, big old tubes for 10,000 watt transmitters. I'm sorry, 4CX 15,000s. It was a Continental 316F. And just, I mean, the hole blown in the side of the tube from lightning.
I had WLIB, which is a 5-tower directional in the swamps of New Jersey. And we had two buildings, two really nice outside buildings burned to the ground because lightning didn't come through the Johnny balls and down into the ground. It took the 1/2-inch sample line down the tower, in through the wall of the building, and caught the inside of the building, which is all that, phenolic board and everything else, on fire. Since it was a weather-tight building, it smoldered for 2 days until finally the heat intensified and started cracking capacitors, and we went off the air. That was the first building that Tom Jones and I discovered that maybe the potential wasn't at ground, and so we redesigned it. But then the second building burned about a year later, and we were like, okay, now it's time to change all of them. But this is where lightning was supposed to come down and do its job through the Johnny balls or through the outside screen, copper screen that we had on the building. But no, it decided to jump to the 1/2-inch sample line and proceed down inside the building. So that was our horror story, twice.
No fun.
I'll send you pictures. No, it wasn't fun.
No.
One electrical engineer told me that lightning does not take the lowest resistance path to ground. Lightning takes the first path it closes to ground.
Exactly.
I agree with that. It doesn't calculate, it doesn't think about it for any length of time, it just does it. And
go ahead,
okay.
Sorry.
I think lightning takes the path, any path it damn well wants to take.
There's some great videos on YouTube showing slow motion captures of lightning, showing the streamers of the leaders coming down from the clouds, but then showing leaders coming up from the ground to meet the leader coming down, and where they close, you get the streamer.
Yeah, it's pretty noisy too. This is more advertising than anything else, but we had a pretty good success about, I guess it's 4 weeks ago yesterday. We've done all the 911 transmitter sites in Mobile County, Alabama, all 11 of them. 4 weeks ago, Wednesday, a major thunderstorm outbreak came through southern Alabama. The image, I may have shared, I think I shared it with a couple of you. There were so many lightning strikes, according to my contact down there, at 10:30 p.m., it looked like daylight. And if you look at a lightning counter of the, well, I don't know if I can get this on here or not. Let me take the screen sharing off. Bottom line is, all 11 of the sites we had regrounded reported a major anomaly, but no damage. and no loss of airtime. Here it is. It maybe you can see that on the screen. I'm not sure if that shows up at all. But all those little red dots are lightning strikes.
Wow.
That's pretty thick. Now that's Mobile County, a pretty large area. But that was in a 1 hour time frame. So one of the towers took a direct hit and it bounced that off. Nothing happened at that site either. We had a lot of situations where there were faults on inbound power, and those were all properly intercepted as well before they got in the building. So we were very happy about that. More questions? Any more questions?
There's a comment about structural steel. My first apartment in New York faced Empire, about 4 blocks away. And one of the most fun during a storm was just watching the antenna get hit repeatedly. And my FM, WPIX and Channel 11 were on the old World Trade. Same thing there. And I don't recall many comments about damaged equipment at either site.
Rich, I can tell you, working at Empire at WBLS on 81, the lightning would literally scale down the side of the building, probably looking for land mobile antennas, microwave dishes, or anything else it could find on the side of the building. So we would literally sit there in the window, Sanchez and I, and watch the lightning skin down the building while it was just looking for a place to go. And I can tell you 2 stories in the World Trade Center. I worked the TV translator up there for Channel 67, so I had to go up and do translator maintenance at 3 o'clock in the morning. When lightning did crack in that building, I really thought the building was splitting in half. It was so loud and so intense as it dissipated, probably more of the thunder than the lightning, but just the dissipation through the building was phenomenal.
Well, the thunder from 4 blocks away was incredible.
Yeah, it's a lightning show. I have so many pictures of Empire with lightning strikes, probably 100 of them.
So the steel is doing this dissipation then?
It did, yeah. It did mostly, it either went down the skin of the building because some of that skin of the building was metal, or that decorative metal, Art Deco metal, or it was going, searching for microwave dishes or whatever else it could find. There's a lot of superstructure, as you know, outside that building. And of course, the old Alfreds, I'm sure 1 or 2 of those Alfreds took a hit, from time to time. But they were all definitely tied into the original structural steel of the building.
And most of those, most buildings in Manhattan have multiple sub-basements. So that stuff goes way down.
Yeah.
I think in Manhattan, everything has to go down to that bedrock, doesn't it?
Pretty much, yeah.
Yeah.
So in
Well,
1972, at my first radio station upstate New York, it was a 1 kilowatt RCA FM transmitter. I was there with my dog. It was time to take the tube out and do maintenance. It was cloudy, but no indication of thunderstorms. I had the tube out, the whole Jesus stick in the transmitter. I think Barry's heard this story before. I had the Jesus stick in the transmitter, and I heard the crack. And you smell it and you hear it, and lightning dissipated on the tower, came down in through the PA cavity of the RCA transmitter and flew around the room, knocking me back underneath the workbench for just a second. And the dog's checking me out. And amazingly enough, the transmitter was not damaged. I put the tube back in and it came back up, but it was scary because I really thought I was going to die.
Happily you didn't.
Well, I mentioned once before, my first station in Massachusetts, going to the utility uselessness, we had a hit that came in through the power line and went from the fluorescent fixture in the ceiling straight down, through the operator's chair to the ground. Fortunately, I wasn't sitting there at the time, but we had a couple of lightning strikes. One started a fire, and the other, hit through the power line.
I'm just going to hold this up for a second. We just had these made. This is a quarter scale model of our electrodes so you can see what they look like. They're actually 4 times the size, but this is a ground rod to us. And some of you have seen this already, but the black material is carbon fiber. And then in the center, we put an electrolytic blend of goodies, some of which I can tell you about and some of which I can't. And it causes this thing to turn into a giant capacitor pretty much for a very short period of time. And it dissipates into a material we have surrounding it that is makes a fish ladder for electrons, we call it, that addresses that impedance mismatch that John was talking about. So that's what it looks like, again, in quarter scale. It works a little differently than ground rod. More questions? I hear nothing.
When or if electrical inspectors see that, how do they accept that? Do they accept that as a rod in the electrical sense or only in lightning sense?
Well, we don't get involved with electrical inspectors because we're never carrying live current. That's the first thing. However, we did run this by our friends at, and I say that very sarcastically, at Underwriters Laboratory, and it all passes UL 467, suitable for direct burial as a chemically enhanced grounding device. If they have a concern, we refer them to UL 467.
And just to comment there, the NEC would consider that being listed for the purpose, as long as the authority having jurisdiction agrees to it.
That is correct. That is correct. But again, it's not carrying live current. So it's only there to dissipate bad stuff. And we've shown it to a variety of inspectors and they all kind of shrug and say, yeah, that'll probably work. So that's that. I have a big issue with NEC 250 anyway. And the NEC has written an awful lot just for the benefit of contractors, it turns out. But when it says in chapter 250, put in a single ground rod and check the resistance to ground. If it's 25 ohms or less, go home. If it's more than 25 ohms, put in a second ground rod and go home. It doesn't say check it after 2 ground rods. Therefore, nobody puts in 1 ground rod. They all put in 2 and don't bother checking it because the code says you don't have to. That's why I'm in this business. My house got hit by lightning in 2015. There's a lot of damage. I had 2 ground rods in place. I watched the electrician put them in. I asked him, and I think I've told this story, some of you may have heard it. I asked the electrician as he was putting them in, I said, what are those? I didn't know what they were 7 years ago. What are those? He says, they're ground rods. I said, what do they do? He says, I don't know. We just have to put them in. That was his entire answer. Well, when the house got hit, I started doing some research and bought my clamp-on meter and found out that the first of many clamp-on meters, as it turns out, the resistance to ground in my house was 540 ohms. Well, I didn't have a ground. That's what it boiled down to. So we eventually developed this product, and I've got the house down to around 50 now, which isn't too bad. But I'm on top of a mountain. Lamar will go along with that. You know what life is like, what grounding life is like on top of a mountain. It's not good. So, but we've been able to get down to 50. Another one we did was on a rocky plateau at 7,500 feet elevation in Bozeman, Montana. And the existing grounding system there for a TV station was at 294 ohms to ground. And when we got finished, we had it down to 6.4. And that was in frozen soil. So that was pretty good. We were happy with that. Now, again, that's clamp-on readings. These are relative measurements. They're not absolutes by any means, but it was a rather dramatic drop in resistance in really, really terrible soil. So it can work. That was the site that when we developed this barrel design, we couldn't go very deep. Our original designs were actually 42 inches deep. What we make now are 18 inches deep, and we put them down only to a depth of 30 inches, and they're working just great. even years after the fact. So sorry for the advertising there.
Tom,
Yes, David.
what do you do when when you walk into a facility and you find out the ground is only a cold water ground?
That's the first thing I do, laugh. I will write up a report very quickly and tell them that they're darn lucky they're still there.
Well, everybody knows it should be a gas pipe.
This is a funny bunch today.
I used to do some work in Alaska, and I'm just curious, what permafrost, how would that qualify as grounding?
Qualify as grounding? How do you mean?
The soil, since it's substantially ice, water, would that be a good grounding?
No.
No?
Frozen water is not a good conductor.
Oh, yeah.
And that's why we've got 8-foot ground rods. The theory was to get to more water and get to unfrozen water. My chief manufacturing partner spent 10 years in Alaska working for Rogers Electric, and he has lots of stories about what you have to do to manage electricity in permafrost. He's on vacation right now. If he was here, I'd put him on the TV, on the broadcast with us right now, but I decided vacation was good for him and John Belk as well, so they're off gallivanting around. The unique thing about our particular design is that it doesn't need water to be a dissipator. And we've proven that by putting these things in dry soil, and they still work. They pretty much have their own moisture supply, but it's the carbon fiber that's the real secret. It's electrons have so many choices on places to travel that it dissipates even into crappy soil.
What is the average depth that a ground rod has to be submersed?
Code says 8 feet.
Is that national code or just your state?
National Electric Code.
Okay.
But it turns out that that's really immaterial. It's just designed again to get to more moisture in the soil. All the dissipation is happening at the tip. There are a lot of specs that say you need to put in, for certain sites, you need to put in 50 feet of ground rod.
And how thick should a ground rod be? What's the diameter?
Typically they are, the inexpensive ones at Home Depot can be as thin as a little less than 1/2 inch. The common is 5/8 of an inch, although in practice it turns out to be 0.58. The UL people point that out to us. In commercial applications, they tend to be either 3/4 of an inch or an inch, and many times they are solid copper when you get into critical commercial applications. In residential applications, they are just copper clad, and a lot of people don't read the fine print on ground rods. It's recommended that they be reinstalled every 10 years. That's what the manufacturers tell you. They are not. Nobody pays any attention to it. And a good example is a story that I may have told already, but it was on Cape San Blas, which is on the Gulf Coast of Florida near Port St. Joe, if anybody's familiar with that part of the country. So there's a wonderful state park out there. I was out doing some photography work and stopped in a convenience store and saw a brand new weatherhead. And so all brand new electric service. So I wonder why this convenience store would have brand new electric service. I happened to have my clamp-on meter with me. I walked over to it, and this is again on Cape San Blas. The elevation I was standing at was 4 feet above sea level. So the ground rod was going into brackish water. Put the clamp-on meter on, got 4 ohms to ground. Real nice. Said something doesn't smell right here. My eye went up, went across to the serving transformer about 50 feet away, went down the ground wire, went over there, put the clamp-on meter on the same circuit on the ground wire 50 feet away, got 1,000 ohms to ground. Said, 4 ohms over here, 1,000 ohms over there. Something ain't right. Grabbed onto the ground wire, yanked on it, and up came an 8-inch long ground rod. The rest had been destroyed by salt in the ground. Happens all over Florida. People have a ground rod, they put it in the ground. 10 years ago, there's nothing there. There's a wire going on the ground, and that's it. They don't know.
Is there a metallurgic specification for ground rods?
It's just I don't know of one with respect to the steel, but it has to have X number of microns of copper on top of it, and that's about it. Although you can get a galvanized steel ground rod, and that will meet code. They will disappear on you as well. Typically, most ground rods that I have encountered that have been in the ground for a while, 10 to 15 years, they're pretty much shot. Many times you have the copper left and the steel has rusted out completely. You have a sheathing of copper in the ground, and that's it.
I know there's mention in the NEC about, and it's up to local jurisdictions, if you can't go down, you can go horizontal.
That is correct. It is allowed. I don't know why, but it is.
I have noticed in a lot of residential areas back in the 60s and 70s, people were using their TV antennas as lightning rods. And with the advent of cable, those antennas have come down. So a lot of homes are not truly grounded anymore.
Well, the ground rod, a home now in code everywhere, you have to have a ground rod, at least one ground rod attached to your meter base. Has to be there. A lightning rod was not ever designed to be an electrical ground for the electrical system in your house. A lightning rod was just to prevent lightning from catching your bar on fire, pretty much. Two different things. Oh, I just got back from Disney World. I've never been to Disney World. I'm 66 years old just about now, another few days. Figured it was time to go to Disney World, and I was quite impressed with Disney World. It's a fabulous operation, and they process so many people so well. But the entire, was it 40 square miles? Every building on it is covered with air terminals, little foot-tall spikes, connected with roughly 2-aught braided wire that goes down to ground rods. They still have a lot of lightning damage, and they kind of scratch their heads on what they're going to do. They've got 4 or 5 different types of air terminals, lots of things going on. I was really quite surprised to see that. And in a lot of cases, the braided wire coming from the air terminals every 10 meters or so on their buildings was laying directly on top of metal roofing and was bolted right to metal roofing. That struck me as kind of odd. I'm thinking that that's not going to be a good dissipation scheme at all. Worse yet, if there was any kind of metal conduit in play in contact with that metal roof, well, now you've infected the entire neutral system of your building. That's not good. I was at Atlanta Airport 3 weeks ago. They've recently installed air terminals all over the buildings. Just like anybody who's been to Tampa Airport, covered with air terminals everywhere. Same kind of deal. They've got conductors not going effectively to a dissipation point. Somebody's getting paid a whole lot of money and not accomplishing anything. Really, really kind of disappointing. Code doesn't talk about this, and it should to some extent. More questions?
Make a comment. I've been installing electric mid-70s.
I'm not getting this. It's not coming through on my end. Is anybody else having trouble hearing?
I was going to say that since the mid-70s, we've been required to drop 2 ground rods 6 feet apart from each other, minimum.
I think NEC said that in 1986, but some local sites may have done it earlier than that. Are they saying 6 feet apart or 8 feet apart?
Right. I always remember.
Well, I'm not getting that at all. Barry, are you getting that?
It's breaking up.
Okay. I don't know. I don't even know who the guest was.
That was Renner.
Okay.
He seems to have dropped off entirely. Probably a bad connection.
Yeah. Okay.
Well, Tom, we sure appreciate your being here, and certainly pass our thanks along to John as well. Very interesting. A lot of points that we need to pay attention to, a lot of hints, and I hope that we'll follow this up with some specific instruction ideas.
I promise you, I will write that article for you, Barry. I promise.
Okay.
I'm just looking at the chat sessions over here. I have a picture on my wall from the night. This is Tim from the 1970s with multiple lightning strikes. One of the targets was a radio station I was maintaining. Not a fun day. No, absolutely not. And Lamar liked it good. Lamar, I'd love to talk to you about your situation in North Carolina anytime you want to talk. We'll exchange information at some point.
Sure, I can arrange for a tour as well.
That'd be fascinating. And you're up in the mountains, so it doesn't get too blazing hot there too fast. What's your elevation?
Roughly 3,000.
Okay, my house is at about 1,800, so not too much, but you're about 4 or 5 degrees cooler than down where the rest of the world lives.
Tom, Rocky Wash on YouTube stream asks that you showed a drum-like instrument and said you put chemicals in. How long does that material last?
We've been installing this for 5 years now. I've been back to some of the earliest locations, and it still is there, and it hasn't changed. Chemically, it hasn't changed. So we've only been doing it for 5 years. To answer the question honestly, that's all the information I can give you. It is primarily a clay-based material. It's not going to go anywhere. Doesn't do a whole lot of movement around, and it maintains its effectiveness. Does that answer the question? I hope.
I hope so too.
All right. So Lamar, I'll get with you somehow. Barry, you can route me to Lamar in some way. Any other chat sessions here?
I think we've gotten pretty much everybody's thoughts.
All right.
Very positive response, Tom, and we will hope to see you again one of these days on Thursday.
I'm still not very polished in these things, and I try to cover too much ground too fast, but I am available for questions anytime. If that helps.
Excellent. Thank you.
Thanks for the opportunity. See y'all.